Okay, so I think we will start off. Okay, am I audible, Vasan Gowda? Shirish, Shirish, you're able to hear me? Yeldo, is it audible? Am I audible? Aishwarya?
Yes, sir, you're audible.
Okay, fine then. In continuation to yesterday's class, okay, so what we will do is, we will continue the discussion and we will try and understand as to what are the concepts involved, okay, and you should be able to see my presentation. Yes, you're all able to see my presentation.
No, sir.
No, sir.
It should come up in a while. Now you're able to see.
Yes, sir.
Okay, fine. So today we are going to continue with our discussions, okay, and we are going to try and understand as to what is your programmable devices, okay, and what are the slight differentiations between them. Now, in my yesterday's lecture, I told you about CPLDs, about FPGAs, right? The complexity involved in CPLDs and the lesser complexity involved in FPGA. So as I was mentioning yesterday, once the complexity increases, the performance also does increase. So once your performance increase, the price of this particular module or the hardware that you're employing will also increase. So price and performance are actually directly proportional. Now here we will see a simple differentiation between SPLDs, okay, and your CPLDs and your FPGAs. Now, the most important thing that you have to see here is, with regards to the density. Now, as you see, density is, varying very much. So, how do we calculate the density? It is nothing but with the number of gates involved. So here you can just see a few hundred of gates available. Then in CPLD you can see, the number of transistors. Now gates are in general, okay, transistors are in general called gates. So as I told you yesterday, in today's generation of your processors, they do have a lot of transistors involved. In fact, transistors are in the count of billions. How is it possible? It is because they are able to shrink the size of each transistor. How are they able to shrink the size of the transistor? Because they are able to place the source and the drain close to each other. Okay, so in fact, nowadays you can find transistors which are being fabricated on 7 nanometer technology, okay, 5 nanometer technology. Now what is this nanometer? As I told you yesterday, this is nothing but your channel length, which means the space between your source and drain. Okay, so that is how they are able to achieve this high numbers. Okay, then with regards to cost, okay, you can see with regards to cost, there is also a lot of significant change, right? As the complexity increases, the cost also does increase, right? Next, these are some of the examples of who is providing SPLDs, CPLDs, and FPGAs. As I was mentioning yesterday about Xilinx, okay, Altera is also a major player. Okay, then you have your Lattice Semiconductor and Actel. So these are some of the major service providers, okay, for your FPGA and CPLD. CPLD specifically to deal with Xilinx, and Altera. Altera is mostly interested in CPLDs and FPGAs. Okay, so these are few examples here. Okay, we will see exclusively about these examples, specifically 22V10 from AMD, right? So this is one of the most commonly used technology. Okay, so we will be seeing this particular example in detail. Okay, then you have examples, say for example a question is asked, okay, give a brief comparison between SPLD, CPLD, and FPGA. So this can be your answer. This tabulation can be your answer. Okay. So you can write how many number of gates. You can talk about the timing. Now, what is timing? Yesterday I was telling you, right, about the rise time and fall time. How much time it takes for the clock signal to go from a lower level to a higher level, right? And how much time it takes for a clock signal to go from a higher level to a lower level. Why do we need clocks? Clocks are generally used for the transmission of data. It synchronizes data, right? So with clock, the transmission becomes easy, right? Uh, so these are few examples to consider, right? So after post-synthesis simulation, the design can be implemented in several different target technologies. Now I was mentioning you about 7 nanometer, I was mentioning you about 5 nanometer. So that is nothing but called your device lengths or channel lengths. The generic term used for it is technology. Okay. Now as the technology increases, the size of the transistor does decrease. Okay, so that is what we are trying to put it up here. Next, the target could be completely a customizing. Now yesterday we discussed what is custom design, semi-custom design, and full custom design, right? So in a full custom design, what do? You try to build everything right from the scratch, and then you try to have a completed product or a complete IC fabricated, right? So that's your full custom design. So I have put up those explanations here, which is nothing but it can be implemented using standard parts, okay, that are available from the vendor. Sometimes this is also called OTC, over the counter, okay, or off shelf devices, which means which are available already. You can take them, or probably you can integrate them with other structures, okay, with other hardware, and you can make, or you can build it as a hybrid device. The next thing that we'll be seeing here is, the standard parts are at the lowest level of sophistication and density with the usage of old-fashioned printed circuit board. So I think all of you would have seen this printed circuit board, right? The green color. Every electronic device will have its PCB, right? So this is nothing but called your printed circuit board. So on this board, we are going to have a lot of ICs, right? Okay, and they are interconnected. A fully custom Asic is at the highest level of density and performance. Now, as we saw the flow chart in yesterday's class, right? So we were discussing about the bifurcations in VLSI. So first bifurcation was Asic, and in between you had your semi-custom, and towards your right hand side you had your FPGA, right? So these are some of the bifurcations that you see with your VLSI design. So as the complexity decreases, okay, the timing taken for the fabrication or implementation of that particular hardware becomes simpler. So we can actually group CPLDs and FPGA, which comes in between, okay, because we can program them specifically, right? So is there an advantage in programming? Yes, of course there's an advantage, because I can have a hardware, I can program it, and I can make it in such a way that if I want to use it as a counter, it can be used, or if I want to use it as a multiplexer, it can be used, or if I want to specifically use it as a for a particular logic, for a code that is written, it can be done, right? So that's the specialty of these programming devices, okay. So CPLDs and FPGAs does have these kind of advantages, wherein you can actually burn programs onto them and actually convert them to whichever possible thing that you would want it to work as. Fine. So here, okay, you have the design flow. First thing that comes is your design entry, then your synthesis, mapping, placement, routing, and then starts your programming. So once everything is done, then you start programming. So let us take it step by step. So in your design entry, okay, you will start off with writing a Verilog code or probably a VHDL code, okay, and you can even generate schematics, technological schematics, and your RTL schematics, right? So using the code, these schematics can be generated. So once this is done, next you will try to in the behavioral simulation level, okay, you will try to synthesize them, which means you will try to give some clocking information to them, okay. And once you feel that everything is fine, okay, at this level, okay, at this particular level, you're trying to go ahead with your timing simulation. Now in this timing simulation, what do we try to understand? We see, or we try and analyze if data is passing from one end to another end in a particular time frame. Is there a delay? Okay, so timing is one such important parameter. Now yesterday I was telling you about placement and routing, right? So what happens in placement and routing? Those blocks which are actually having more interconnections are actually placed closer. The reason why we do this is, say for example, block A and block B, okay, they have a lot of interconnections between them. So it is logical to actually place them close to each other. Suppose let's take the other way around. We place it very far, and the connecting wires running between them will actually increase your capacitance, your resistance, and indirectly it is going to affect the performance, right? So how do I say the performance is affected? It's because the data is not being delivered at a particular set of time. So ultimately this step, your placement and routing, plays a very important role. Next is your program. Okay, so here you can actually program using your SRAM or your flash technology, just like your pen drives, right? So even your pen drives are programmable devices. Whichever data that you want to send or you want to burn, it can be done, right? So pen drives use a flash type of memory. Okay, then in cables you will see major two types of cables, okay, which is serial and parallel. Both do have their advantages and disadvantages. Serially means there is a transfer of data bit by bit, but then in parallel you can find that the data is being transferred at one shot. You can probably transfer 8 bits, 16 bits, 32 bits, right? So that's the specialty of parallel type of programming. But then uh, as you know, the complexity also does change. Okay, so that is the added complexity with your parallel type of programming, right? So the two most common targets, okay, which is nothing but your FPGAs and ASIC. So this is the major two differentiations in VLSI design. The design is mapped into specific target, which is nothing but technology or channel length, and is placed into specific parts of target ASIC or FPGA. So what are we trying to do? We are actually trying to build a mask. Yesterday I told you about the mask, right? So these masks are built as a prototype, and once everything is fine, once the timing verification is done, okay, once they find that everything is up and running, then they will start producing it in mass, okay, which means in large they will start producing it. Now here, during routing, the selected components are connected to each other using available paths. So routing is nothing but connecting between two particular modules or two particular circuits. Okay. In case, okay, let's say for example, your in case of an ASIC, let's take ASIC, the router design is utilized for generating a photo mask. Okay, this is what I was talking about, which will be utilized for manufacturing the ICs. So once the mask is ready, you actually give it to your fab centers or fabrication centers, and they will enable, okay, using your bit file, your GDS2 file. Remember yesterday I told you about GDS2. Can someone tell me the full form of GDS2? Yesterday we had discussed, right? Can someone tell me the full form of GDS2? Eldo or Vasant or Aishwarya, anyone? Anyone can unmute and you can tell me what is GDS2. We discussed in yesterday's class, right? So it is nothing but your, yeah, Vasant, tell me. Vasant, go ahead. Yes, go ahead. What is GDS2? Okay. So it is nothing but your graphical data schematic for information interchange, right? So that is your GDS2, right? So you can probably make note of it. In case of an FPGA, the router design is translated into a bit file. Now this is the bit file, this is the GDS2 file which I was talking about for the programming of selected cells inside FPGA. So it is just like coded. Okay, so these bit files are coded and you can use them, okay, for your uh, purpose of manufacturing IC. So here I have put up few examples, okay, as to how it's going to look. So if you see, you know, this is the density of your PCB. Okay, you can find a lot of transistors, you can find a lot of capacitors, you can find a lot of switches. Okay, so all these are part of your complex hardware, right? So there are few concepts involved here, which is time to market, which is nothing but how much time is taken for a product to be released into the market. Okay. So as I told you yesterday, I was discussing about the engineering hours, right? So once they start designing, they start building a circuit, they try to simulate it, they try to check if everything is fine. If it's good, then they will proceed with the manufacturing of a prototype. Now what is a prototype? It's going to be a testing type. So just one product is produced and they try to do a check on all of them, which means all the tests are run onto it. If it passes all the checks, then they will get into mass production. Okay, so I can quote one of the examples that happened with Intel. Okay, way back in 80s. um, they had actually produced an IC, and 70% normally in VLSI industry, 70% of the time goes into testing and verification. Okay, so which means a lot of money, a lot of time is invested. About 70% is invested only on testing and verification. So now, um, due to some reasons, okay, probably they didn't have a proper check on it, they just released it into the market, and then people started facing issues with the processor. They started complaining. So just because of one step, okay, just because they were not able to properly check their IC, okay, their share market went down. Okay, so this can be an impact on company if testing and verification is not done. So this particular step is very important. Now if you are in search of a job, okay, you will be you will be seeing profiles as to testing engineer or verification engineer, right? So wherein you will be put up in departments where prototypes will be sent to you and you have to run checks on it, right? So there is a lot of demand for this particular market. So when I say time to market, it means that how much time is the company taking right from designing to bringing it into a product type and releasing into the market. So this whole time is taken as time to market. Then you have something called NRE, which is non-recurring engineering cost. Okay, so in ASICs you do have higher. Why? Because you are custom designing it, right? Here it's going to be very low because you're just using off-the-shelf materials, right? The design flow is going to be simple here, and here it's going to be complex. Accordingly, you can see with respect to unit cost, with respect to performance, as I told you yesterday, the performance of ASICs are significantly higher. Whereas for FPGAs, it is not as high as ASICs. That's because we don't custom build it, right? We just use components which are built by someone and then we try to assemble them. And then you have your power consumption. It is low here because we take care of even power consumptions parameter. Then you have your unit size. Unit size is going to be medium and here it's going to be low. Why is it low here? It's because we are building it for a custom design, which means every market will not need the same chip, right? So this particular chip will be used for a particular purpose. So they cannot mass produce it. So the requirement might be just with a single company. So hence you can find that the unit size, or the number of units produced, is very less. Fine. So here you can see another flow diagram, okay, where you can see design requirements, conceptual design, okay, ESL design, then your RTL and constraint design, FPGA synthesis, place and route, program device. This is just for your understanding, okay, that I have put up here. And one such example of an IC, okay, from Intel Xeon series. And you can see it starts off with the design, synthesis, implementation. If everything is fine, it goes into programming. Okay, in the programming, in circuit verification, back annotation. Back annotation happens with timing verification. So if suppose I wanted the data to be transmitted in 10 nanoseconds, and it's transmitting data after 20 nanoseconds, then I have to rework. I have to come back and I have to rework on design implementation. Always remember, say for example, if there are about 10 steps, you found an error at step 5 and you're moving on to step 6, okay? If you keep that error and move on to the next step, the cost of rectifying the error in the next step, okay, actually doubles, or it becomes, much higher than the cost required to get the error rectified in the same step, okay? So it is always a must for you to verify at each and every step if there is any errors involved. Okay, so that's the reason you have something called back annotation. Next, yeah. So once it's done, once it's programmed, then you can go ahead with the testing. Okay. So this is actually implemented using one prototype device. If it's fine, then you go ahead with the others. So the next topic that we are going to discuss is about hardware description languages. As I told you yesterday, there are two major things that we will be looking into, Verilog and Vhdl. So our concentration more will be on Verilog alone. Okay. So HDL is a type of text which documents the circuits. Okay. So if I have to say the operation of AND, then I have to write it as A and B, right? So this text is actually typed in Xilinx as a program and it is implemented, right? Then it doesn't have any graphics, right? It doesn't have any graphics while programming because we are actually putting it in the form of text, right? HDLs lead to a top-down design methodology, okay, specified and tested at high level. And HDLs are designed to be technology independent. So what do you understand by technology independent? It is nothing but, remember we told or we discussed about the channel lengths, right? So it is not dependent on any kind of technology. So whatever program I write, I can use it for any technology, for any um, I can use it even for 45 nanometer, or probably I can use it for 90 nanometer or 180 nanometer. So it is technology independent. Next, you can see here that you have HDLs which can describe a digital system at three different levels. So the first one is behavioral, data flow, and then structural. Okay, so these are the three main um, you know types of levels. Of course, there are few other bifurcations as well, but then we will be focusing on these three mainly: behavioral, data flow, structural. Okay, so behavioral is in the form of functional description, data flow will have logical equations, and in structural you will be actually mentioning nmos, pmos, so you will be naming the components, so that's why it's called structural. And in data flow you will be using the truth table. Okay, and in behavioral you're going to use the equation. Okay, you're going to use the functional description equations. For example, sum will have an equation, carry will have an equation, so you will use that equations. So these are the two most popular HDLs. As I told you, Vhdl and Verilog. So Verilog was a proprietary language in 1984, and later, you know, it was made open source by Cadence. Cadence is a software where we design the circuits, where we put layouts, where we simulate. Right? Yesterday we had a discussion on Cadence. So in order to create a vendor independent language and to prevent industry from shifting to Vhdl, so Cadence actually wanted people to use Verilog. So they didn't wanted them to use Vhdl. So instead of having it as a proprietary, you know, software, okay, or proprietary language, so they tried to actually make it open source so that it can be used by everyone. So if a question is asked with regards to differentiate VHDL and Verilog, these differentiations could be your answers. Okay, where VHDL was developed by the defense, okay, U.S. Defense, Department of Defense in '87, and this was Verilog was commercially developed and became an IEEE standard in '95. So way back, we were actually using both VHDL and Verilog. But as days pass by, slowly we are migrating, and we are stressing more on Verilog. That's what I want to say. Next, VHDL has a strong typecast, which is based on ADA language and is case insensitive. Now, this is very important. Case insensitive. So you can use an uppercase or a lowercase and program. It doesn't matter. But in Verilog, it does matter. Even if you write instead of small c, if you write a capital C, it's going to take up as an error. But in VHDL, all that is nullified. Okay, in VHDL it is not case sensitive, but Verilog it is case sensitive. Now here it is structured and is for large and complex systems. So if you're having a large system in mind, then you can go for VHDL. Now here in Verilog, it is very simple, less syntax and fewer constraints. So the rules involved in VHDL is very high, okay, compared to the rules involved in Verilog. So you will see them actually one by one. We will discuss as to how VHDL has n number of rules, and Verilog has made it simple in actually determining how things need to be worked out. Right. In addition, there are system design languages such as System C. So not only VHDL, not only Verilog, you have something else called as System C. You have also something called as System Verilog. Okay. Now, if you look up for jobs online, this can be your requirement. They will ask you, are you good at System C? Are you good at System Verilog? Okay. Or probably are you good at front-end designing? Are you good at Verilog? Or are you good at VHDL? Right? So these are going to be your target questions. Now, why do we use them? Ultimately, we use them for describing your systems, right? Now, we saw describing of systems can happen with your behavioral type or data flow type or in structural type, right? So using these, you can actually model your systems. So the behavior of your system is actually modeled or it can be programmed using your Xilinx. Okay, right. So this can be your differentiations.
ಅವ್ರ ಜೊತೆ ಒಂದ್ಸಲಿ ಕೋಆರ್ಡಿನೇಟ್ ಮಾಡಿ.
So here you will actually find that your system C and system Verilog, okay, are also part of this VHDL and Verilog. Okay, so it is a bifurcation. So these languages are primarily used for verification and validation. Okay, so what is happening here in verification and validation? As I told you, 70% of the time, okay, your your time and money is actually invested in verification of any process, right? So they help in reducing the design cycle time for large systems. The design problems become evident in the early stages instead of becoming obvious during system integration. So as I told you, in the initial stage itself, you should be able to rectify your problems. Do not keep your errors prolonged or for the next step. Okay. So different blocks of large system are designed by different teams during the initial design process. One team can make use of system level description of a block that is being designed by the other. So here co-design is needed. Say for example, team A is designing on something, then team B should be able to use it. It is not that whatever they design is going to be specific and unique for themselves. It should be as a teamwork, wherein any module that is being designed, okay, they should be able to call it and use it. In addition to system design languages, there are tools which are emerged which can convert models written in non-HDL directly into hardware. So there are some software, okay, where you can directly convert whatever code that you have into a specific hardware. Now these are some of the strengths of HDL. You can go through them, and differentiation between the other programming languages. Okay, so what do you see here? What is the strength of HDL? It actually helps in concurrency, isn't it? And then it helps in bit manipulations. It helps in module representations, timing constraints. Now this happens in your synthesis, right? And here you have structural representation support. So what are all this? These are nothing but your strengths of HDL. How you can use them one by one, we will actually look into it. Then in your programming language, okay, you just have data structures and language support. So these are the only two. So if you see, actually HDL is a more complex programming structure where you have to describe a system, right? You have a system, you need to describe and you need to put it across. So if something is not fine, then you cannot actually you cannot model a particular system, right? So unlike other programming languages, the constructs of HDL are tailored for the purpose of simulation and synthesis. So that is one important thing, right? So what we will do here is you probably go through these notes and I'll be connecting back with you in some time. Okay. So we will probably end this meeting, okay, and we will connect back in some time. Thank you.